thesis in this room. So, are we allowed to ask questions? Probably nothing. Probably we are, but it doesn't count. She came from a very standard trajectory, which was Sharif to ISL, to Caltech, and then University of Washington, where she's a professor. Great.
Thank you. Okay, hi and good afternoon. It's a pleasure to be here at Stanford. It's always great to visit, and yeah, it's fun to think of my thesis defense, which was in this same room a long time ago. Okay, so today I'll talk about recovery of simultaneously structured models, which basically means whenever you would like to find a model given data which has more than one kind of structural prior assumption on the model. This is joint work. The work I will present is joint work with my student, Amin Jalwadi at the University of Washington, our collaborators at Caltech, Samit Oymak, who's a graduate student, and Babak Kasibi, another ISL alumni who's a professor at Caltech, as well as Yonina Eldar at Technion. Okay, so the idea of structured models is actually a simple but very, very useful idea that has been exploited in many different areas. So the idea is that you are interested in models or signals that have very few degrees of freedom or inherent dimensions, where while they are living or they are actually in a very high dimensional ambient space. These kinds of signals or models arise very naturally. In some ways, people say that principles of nature encourage various forms of sparsity, simple representations, etc. And they're also very useful to exploit in many different settings and help us in to achieve many modern goals and objectives in different tasks. For example, in data acquisition, when you want to acquire data or samples from a physical phenomenon, making use of the underlying simplicity of the model is very important, and that's given rise to the big area of compressed sensing. Exploiting simple structures is also important in the storage and transmission of data when you're gathering samples, storing them, and compressing them, and then sending them, as well as in mining data, for example, in the areas of machine learning and statistical analysis. So one question that comes up is that in order to be able to exploit underlying simple structures in data, we need good computational models and methods. So we need a way to systematically ask for a model, a solution to an optimization problem, to have the structures that we want. So we need computational methods for recovering underlying simple models. And especially in the regime that we're going to focus on in this talk, is when we don't have too much information, so given limited information. It could be because we have only a few number of samples, or samples are low, or it could be because obtaining measurements is costly, for example, in medical imaging, or it could be simply that we have a lot of data, but the inherent dimensions are extremely large. So you're still in a regime that your data is going to be very limited. And the type of questions we are interested in is, can we construct convex regularizers or convex penalties, norms, terms that would encourage the structures of desire in our solution? So some examples of the typical structures we look at are as follows. The most common ones are, okay, I'm looking for a vector. For example, it could be a set of coefficients representing a model, and this vector is sparse. So let's say it only has k non-zeros out of possible n number of entries. This comes up in compressed sensing. It comes up in the lasso regression in statistics, and many other areas. Another variation on this idea is group sparse vectors, which are, again, vectors. It's a variation on sparsity vectors where you have non-zeros, but they're grouped together. And that comes up in group lasso and also in signals that have joint support, recovery of signals with multiple measurements. Another type of structure we're interested in comes up in matrices that have a small rank, a small number of non-zero singular values. Comes up in, for example, collaborative filtering, such as recommender systems. You may have all heard of the Netflix problem, for example. Inherently low rank but very, very large dimensional matrix that encodes ratings of users for movies. Also, for those of you in control, it comes up in system identification. You deal with low rank, for example, Hankel matrices that capture low-order dynamical systems that fit certain input and output dynamical data. Also, in the problem of phase retrieval, that I'll talk a little bit more later in signal processing. Then what else? I mean, these are the typical structures one sees quite often. More recently, there have been structures that actually combine these existing types of structures. For example, you can say, I'm looking for a matrix that is a summation of a low rank part and a sparse part. the low rank part encodes some part of your model and the sparse part something else. So for example, that arises in principal component analysis with outliers. So the rank part is the principal component part and the sparse part are the outliers. And that has applications, for example, in face recognition. So these are some examples of models that have been studied in the literature. I'm going to actually add one more to the list, which is a new one we're going to look at in this talk. And that is an object that is simultaneously, for example, sparse and low rank. A matrix that is simultaneously sparse and low rank. So it has a lot of zeros in it, but also has a small rank. And this kind of matrix, in fact, is pretty simple if you think about it, because it has many, many zeros. It includes lots of zero blocks, only a small non-zero block, basically. And that non-zero block also has a low rank. So it's a very strong structure. This one comes up in, for example, sparse phase retrieval, which we will look at now. So one motivating application for a problem in which you have a matrix that is both sparse and low rank comes up in, broadly in the area of quadratic compressed sensing. So you have a signal that's captured by a vector x naught, and you have measurements of the signal captured by this inner product with this measurement vector a sub I. And usual compressed sensing looks at linear measurements, so you have these measurements. But in this case, quadratic compressed sensing, you basically end up with measurements that are quadratic in the signal. For instance, in optics, what happens is that you have a linear measurement, but the phase of the signal is lost. You can only measure intensity or amplitude of the light, but measuring phase is very difficult. So you end up with measurements of this kind, and this is absolute value, and if it's a complex number, it's just the magnitude. Now the question is, can I recover a k-sparse signal given a bunch of these measurements? And why does it relate to low rank and sparse matrices? Well, in an interesting way, and this technique, by the way, is very typical in these class of problems. It's called lifting. So your sparse signal is x naught, but you define a matrix that is rank 1, and it's basically outer product of x naught and itself. And if you then square both sides of this guy and write it like this, it is now linear in the variable matrix x. So now you have linear measurements in x, but x has to be positive semi-definite, it has to have rank 1, and satisfy linear constraints. And so in several papers, this kind of reformulation of a phase retrieval problem has been explored, including this recent paper by Emmanuel and others. And this is one motivation for a problem in which you end up with matrix that, so far what they explored did not include the sparsity of the signal. They were simply looking for rank 1 matrices that are PST and agree with linear measurements. But if you actually add the assumption that x naught is sparse, then you will be looking for an x naught that is rank 1 and block sparse. So now it has two structures. There are other applications in which more than one structure occurs. In fact, some of them in cluster detection in networks, there's a recent reference on that. But in fact, you can think of in many problems, even in machine learning, for example, that you have more than one prior on the desired object. So you're simply thinking of, I need it to be this, and this, and this, and so this framework includes all of those. Okay, so this is the type of question we are interested in. We have, basic setup is that we have a structured model x naught in Rn, n is the ambient dimension, can be very large. We have linear observations, so G is a mapping from Rn to Rm. I can simply think of it as an m by n matrix. M is usually much less than n, and m is the number of measurements, the number of linear measurements we have. Given the measurement map and the measurement vector, and knowing the structure of x naught, we want to find x naught. So that's the canonical problem. And recent research has looked at this, many versions of this canonical problem, and often the type of questions that are being asked are, if I have limited measurements, how many are enough for me to be able to reconstruct x naught? How many are enough in general, and how many are enough if I ask for a computationally efficient method, or tractable method? And so I would need to find some way of characterizing this m, and correspondingly an optimization, a tractable optimization method to reconstruct x naught. So for the purpose of this talk, we will be, for our measurement model, that is this mapping G, we will restrict ourselves to a very special case. However, it's still an important case to study and allows us to give generic results. So in this talk, we're going to assume that G are the so-called generic measurements. So G is represented by an m by n matrix, where every entry in the matrix is an IID random Gaussian variable, standard normal, so zero mean and unit variance. So it's special, but you will see that actually it says a lot about general classes of measurements as well. Okay, any questions so far? Okay. So some of the examples of these problems that are very familiar, so this is again a review of literature, come up in, for instance, compressed sensing. Again, going back to k-sparse vector, if I ask this question, if I were to solve this optimization problem of minimizing the cardinality of X, number of non-zero entries in X, also known as L0 norm, which is not a good name, but everybody uses it, subject to linear measurements. If I were to solve this problem, how many constraints here would be enough for the solution of this optimization problem to be the desired X? And the answer is it would be order K, constant times K, where K is the sparsity. Doesn't depend on N. So with high probability, with high probability, I mean over this measurements G, because remember, G's are random Gaussian measurements. Okay, so good. However, this is a non-convex problem, and it's hard, and I can't solve it. So what typically people do is this convex relaxation. You replace the cardinality function with the L1 norm subject to the measurements, and this is now a tractable convex problem. Now, how many measurements do we need for this problem to recover X naught? The answer is K log N over K, which basically is very close to K, because log N is a very small number even for a large N. So this result itself was a critical result that enabled this whole area of compressed sensing. Goes back to probably even older, but was studied in Candace Romberg-Tau in 2004, Donovan in 2004, and others. And it's amazing because you're going from a non-convex problem to a convex relaxation, and in terms of number of measurements, you're only paying a log factor, log n factor. So interesting. Similar thing happens when you look at low rank matrices. So if X naught now is a rank R matrix of size n by n, I can write this problem. Look for the minimum rank X that agrees with my measurements. How many measurements do we need here? The answer is order of n times R, where n is the size and R is the rank. And this comes just by counting degrees of freedom. And it's easy to show. The convex relaxation corresponding to this problem is minimizing a particular norm of the matrix, which you may be familiar with, is the sum of the singular values of the matrix, also known as trace norm, nuclear norm, or Schatten 1 norm. And this convex relaxation has been shown, actually has been shown in this paper by Candace and Plan, that also only means order of n times R Gaussian measurements to work. So interestingly, there is no gap other than a constant. So this works really well. It's very close to the minimum number of minimum information you need to recover that object. Okay. So now, in this talk, we're going to look at another case in which we have more than one structure in one object. And the hope is, because I know more than one piece of information about the object, I should be able to recover it from much less measurements. I have a lot less degrees of freedom. So let's see if indeed we can use that, we can exploit that joint structure. So what kind of convex program should we consider? Well, the most typical is, well, okay, suppose I have S structures and each of them have a known norm or penalties that actually promote each of those individual structures. Why don't I combine these norms and do a multi-objective optimization? I'm trying to minimize all these norms at the same time. So let's write down this problem. And I can use any function h here that is monotonic with respect to the cone Rs plus. So a function that's increasing monotonically. For example, one example of it would be considering the usual case, which is summation of lambda I norm xi with some regularization parameter lambda that you can vary and choose the best one, etc. You can also pick the pointwise maximum of these norms. And in this case, the constant in front is actually related to the norm of the solution. So any of these work, and there are other functions as well. So we are going to look at how does this optimization program perform in terms of number of measurements. Now, the correct way to think about it really is, instead of worrying about the function h, what we really care about is that we can think of it as a Pareto optimal surface representing the set of all, well, okay, so let's look at this. Let's consider we have two norms, and norm 1 is here, norm 2 is here. And I'll put a point here for every feasible combination of norms that agrees with my measurement. So that's the set of achievable values. And that set will be convex for this problem, and the boundary will be something like this. And that's the Pareto optimal curve. So if x0 that I want to try and recover lies on the Pareto curve, then I can always construct, for example, a hyperplane that gives me those optimal lambdas that allow me to recover that x0. If x0 does not lie on the Pareto optimal curve, then no convex penalty will be able to recover it. No combination of these norms will be able to recover it. So if, for example, the number of measurements is this much and low, then the curve looks like this, then I cannot recover this x0. So the question basically becomes, how many measurements do we need for x0 to actually lie on the Pareto optimal curve? So we want to bound that to the lowest number of measurements needed for any of those optimization programs to be able to find that particular x0. Okay, so our results are going to be the following. First, we are giving very general theoretical analysis for a given set of norms of the performance of this optimization problem. We are going to show that when you're combining these convex penalties, there is a fundamental gap in terms of number of measurements compared to the best possible. And we illustrated in the special case of low rank and sparse matrices. So that's the goal. And we need a couple of definitions. So we are going to look at general norms, but these norms have to satisfy a few assumptions that are not very strict, because all the known norms that we typically work with satisfy these assumptions. So we're going to assume that the norms we are using are decomposable. Decomposable means a norm is decomposable at the point x if there exists a subspace T, which in a sense generalizes the notion of support, and a vector E in that subspace, which generalizes the notion of sign, such that the subdifferential of the norm decomposes or can be represented like that, which means every subgradient of the norm at point x has a projection onto subspace T that's equal to the sign vector, and has a projection onto complement of T that has dual norm less than 1. Okay, so it may look a little bit complicated, but basically it says that your subdifferential of the norm, the directions in which your norm is decreasing, have a nice structure and decompose into a T and a T pair. If you think of, for example, L1 norm, this is in 2 dimensions, this is the L1 norm ball, and this is, let's say, point x that we want to try and recover. At this point, the subgradient of the L1 norm will be vectors such as this G, whose projection onto the support of x, which is this axis, is E, which is the sign vector. So what do we mean by sign vector here? This is just 1 and 0, so its sign vector is also the corresponding 1 and 0. Sign vector for this guy will be minus 1 and 0, etc. Okay, so that's T. Projection of G onto the orthogonal complement of T is this blue vector that has, it's any vector that has a value between +1 and -1. So it's infinity norm, which is dual of L1 norm is bounded by 1. So anyway, it says that the subdifferential here has this nice decomposition. And this definition is already appeared in work of Candace and Rick, as well as has been used in work by Martin Wainwright, Sahan Eliakwan, and also John Wright and Guimond. So several people have already used this characterization. The known norms that we typically use are all decomposable, most of them. Okay, so now I have a question.
The subspace T depends on x.
Yes, it does actually. So if I want to be very careful, I should actually put T sub x and E sub x. But let's just drop the x. So at the point x, there is a T and there is a... Yeah, it does because, for example, if you just think of vectors, even the support of a vector depends on that particular vector, which indices are non-zero. So, okay. So now we have a bunch of structures. So we have a bunch of these norms, and all of them are decomposable. So I have a bunch of these subspaces T and these sign vectors E. So a couple of definitions about this. Let's see. We define the joint support. So this is going to play an important role. Joint support is the intersection of all these subspaces T. This one is S. So the intersection space. So for example, if norm 1 has this at point x0, let's say this is x0, your support space is T1, and with respect to norm 2, it's T2, then the intersection is this, and x0 still lies in that intersection. We denote it by T cap. We also need a couple more definitions, so we project these sign vectors onto the intersection space, and we call it E cap 1 and E cap 2. And there's a notion of angle, which measures the angle between the sign vector and the joint subspace, which is basically norm of that vector divided by the original vector. It's the cosine of the angle between. Basically, we are trying to encode the relative geometry of these norms. Because as you might imagine, they would help each other a lot if their information was orthogonal, and they wouldn't help much if the information was very redundant. So it tries to capture that. Okay, so now this is the first result. Suppose the norms are decomposable, and I solve this optimization problem that combines these S norms with a monotonic function H. This program fails to recover X naught with very high probability if M is less than something. Then that's the bound. So what is the bound? This is N, ambient dimension, that's a constant. And as you can see, it has to do with the length of subgradients when they're projected onto the intersection, so in the intersection of the supports, right? So length of the subgradients projected onto T cap. So this doesn't seem very intuitive. Let's do something about that. If we make one more assumption here, then the result becomes nice and interpretable. The assumption is this. Let's assume that the E cap I and E cap J for every pair I and J have a positive inner product. So that means all these sign vectors, that actually all the sign vectors with X naught themselves have positive inner product because they're the sign of that vector. But we're going to take one more step and say all these sign vectors themselves have positive inner products. If I do that, and so it's not unreasonable, and if you verify it for, again, typical norms, it holds for combination of L1 norm, L12 norm, and nuclear norm, etc., it holds. Under that assumption, our bound becomes this. So the program is going to fail if M is less than something times minimum of the dimension of the TIs. I'm going to talk about these guys in a bit, but basically they're bounded by constants, so you can think of this whole term as a constant. So what this result says is that the number of measurements needs to be bigger than this value, at least, for recovery to work. But it's a bit surprising, because we would have expected the number of measurements we need to recover would be proportional to the dimension of T cap, the intersection space, because that's where X naught is. And X naught is actually quite low dimensional. But we are stuck with the minimum of the dimension of the TIs, and if all these TIs have a high dimension, this minimum could be very large. So we see conceptually a gap between this and this. So we don't get what we think is the right measure for complexity of object. And we have an extension in which we can add extra cone constraints. For example, let's say the matrix is also positive semi-definite. It doesn't help very much because it only actually affects this constant. You still have this term there, even if you add a positive semi-definite constraint. Any questions? Okay, so a little bit about those constants that appeared. So they're a little bit messy. This kappa I captures something, some relation between the energy of the sign vector, the Lipschitz constant of the corresponding norm, etc. But the interesting thing is that even though we cannot give a very nice interpretation for the whole quantity, when you compute it for L1 norm, L12 norm, and nuclear norm, it's all small constants. It's actually equal to 1 for L1 and L12, and it's between a half and a 1 for nuclear norm. So for our purposes, we're going to treat it as constant. So the sketch of the proof of this actually gives a little bit of insight into what's going on. Is that it's not hard at all. So you write the optimality condition for the optimization problem. So it will be something like there exists a Z such that the adjoint of G at Z equals G. So think of this as just a matrix G and this G transpose, right? So G transpose Z equals G. G is a subdifferential or is a subgradient of the objective function at X naught. And simply using the rule of composition of subgradients, this G is a linear combination of subgradients of the individual norms with some positive factors Wi. So, okay, so we just plug this in here, and then we project both sides of that condition, this equality, onto T cap. That's the desired space where the object lies. Project it onto T cap and you get this. On the right-hand side, the projection of GIs onto T cap is nothing but the sign vectors because of the decomposability. And from then on, there's a couple more steps, which is basically noticing that this is a random Gaussian matrix and projected onto a subspace. It is still a random Gaussian matrix. The Gaussian distribution is invariant. And we have very good bounds on upper and lower bounds on singular values of a random Gaussian matrix, which we can use right here. And then we get the bound on them after a couple steps. Okay. So what does it mean, for example, in the case of sparse and low rank matrices? In the case of sparse angle-rank matrices, we can actually concretely put numbers. So this axis shows how many measurements you need to recover an n by n matrix with a k by k subblock in it that has rank 1. So what's the degrees of freedom? Degrees of freedom of such an object is r times 2k minus r, so it's on the order of k times r. Note that n doesn't show up. These are small numbers, basically. If I write a non-convex optimization problem with rank in it and with number of non-zero columns and number of non-zero rows, all of those are non-convex. This program, just by doing a counting argument, we can show that it needs on the order of k log n plus kr measurements to give us the correct x naught. The convex relaxation, let's consider this one. So replace rank with nuclear norm, or in this case, because I'm putting PST, it's just trace. Trace plus a 1-2 norm of the matrix, and including a positive semi-definite constraint. In this case, it's going to be order n times r, based on the analysis we just showed. So there is a big gap potentially between these two. This is order k, small numbers k and r, but n can be very large. So this kind of convex relaxation does not have a very good sample complexity, or does not allow good compression of your desired object, which is a low rank sparse matrix. So that's one conclusion. We also looked at some variations on this. So for example, a general matrix, a PST matrix with arbitrary rank, and a PST matrix with rank 1. Let's look at this last one, a PST matrix of rank 1, which is actually what comes up, for example, in the sparse space retrieval problem. There we need, the non-convex problem would need k log n, basically, and R bound shows that the convex relaxation requires at least minimum of k squared and n. R is equal to 1, right here. So it's interesting. Another way to interpret the result is that if you were to only use one piece of information at a time and write down an optimization problem and solve, and then see how many measurements that each of those optimization problem needs, what you are doing by combining this is equivalent to just picking the best among those. So combining these structures did not buy you much, or didn't buy you anything, basically, other than a constant, with respect to just using individual nodes. So some numerical verification of this. We ran some experiments to try and see what happens. So typically in these cases, the way to do experiments is that take every cell in this image. For generating every cell, we make 100 random matrices of the desired, with the desired structure. Let's say n by n has a k by k block in it as rank r. And then we generate random Gaussian measurements of that particular matrix, then set up the optimization problem, solve the optimization problem, find the solution, compare it to the original x naught, and see if you recovered the true x naught or not. And with some threshold on the error, we would declare recovery is correct if the error is below 10 to the minus 4, let's say. And then out of those 100 runs, we would mark a black spot if all of them failed and a white spot if all of them succeeded. The gray region shows certain percentage of time you succeeded or failed. So interesting is that typical to what people see in compressed sensing or other related problems, you see a sort of a phase transition. You see that it's not like very sharp, but you see a clearly black region and a white region and a transition region in between. And what our bounds are predicting, for example, in this last line of this table, is minimum of k squared and n are the minimum measurements required. So in the plots, when I'm fixing k, sorry, the k is fixed, k here is equal to 8, and n is increasing, so this is the dimension of the matrix. So initially, I would expect to see something that goes linear, increases linearly with n, and then relatively constant with n, because after that, k squared is the dominant term, and k here is fixed. And so roughly speaking, that's what we see. That's first increase phase and then relatively flat. It actually doesn't look completely flat, so possibly there's a log n factor here too, but our bound is a lower bound, so it doesn't capture that necessarily. So there might be. And the two plots show that if you change the lambda, the general behavior is the same. So it's not that the program fails because you're picking bad lambdas. For any lambda, the same story will hold. So here's another example. In the previous example we had, the objective was the summation of the two norms. Here we are taking this pointwise maximum of trace and a 1-2 norm, and the regularization parameters are these very idealistic values that actually depend on the norm of the solution. Usually we don't have these available, but even if we have, we still have this same behavior. So this shows the number of measurements. It's divided by this angle parameter theta squared just for ease of plotting, but that doesn't really play any role. And this is n, the size of the matrix. We also here showed the green curve in the previous plot, and here is just the empirical 90% failure curve. We just wanted to kind of trace out and see below which curve are you failing 90% of the time. In this figure, we did that twice for two different recovery thresholds. So for 10 to the minus 4 for the green curve, and a much larger number, like 10 to the minus 2 for the red curve. And they overlap mostly. So that basically means that indicates that whenever recovery is failing, it is failing badly. So in this black region, it's not that the error is tiny. Whenever we declare it didn't recover, the error is often very, very large as well. So it is like a phase transition. So, okay. So another experiment is the case of one of the other rows in that matrix we had, in the table we had, one of these where the scaling with the n was predicted to be linear in n, so it has to be at least r times n. And here we see linear with n scaling for that particular problem. Okay, so any questions? I will talk about one, another related topic, but any questions about the recovery? No? Okay. So it turns out there's another question that people have been interested in signal processing and in statistics, which is the question of how well can I denoise a signal? How well can I get rid of additive noise in recovering a desired signal? So here the model is very simple. I have y are my measurements, x0 is the original signal, and z is noise. And even if z is just Gaussian IID noise, how much noise variance can I tolerate in recovering x0? And I'm basically trying to think of prior information or structure on x0 and see how good those structures are. So we will be looking at this, the problem of minimize the L2 norm between y and x, plus a structural term or norm or penalty that tries to encourage the prior information on your signal. So if this was just a one norm, for example, this problem has been classically studied in 90s and 80s actually even by various people. Denoising properties of L1 norm have been understood. More recently, denoising properties for the nuclear norm have been understood. And they basically perform well. And the type of error measure people are interested in this kind of questions is the following. Usually people look at this denoising risk. Oh, by the way, this thing has another name in optimization community, and many of you may recognize this, simply the proximal operator of this function, right? It's the minimizer of a L2 plus the function. Distance to a fixed y plus the value of the function. So it's nothing but finding the proximal operator. Okay, and we judge the quality of this x hat by looking at this error, typically, which has good statistical meaning. So the error is expected value of x hat as a function of the lambdas and z minus x0, L2 norm squared, divided by the variance of noise. And you look at the worst case noise, so the maximum of this value over all noise variances. So that's the maximum possible MSE error that you can incur. Okay, so that's called denoising risk. And so even though this is a different line of research and people are proving bounds on this denoising risk, what happens is the analysis is very similar and quite parallel to the recovery of a structured object given a number of random measurements. So there's no measurement here. Here the noise is random, but the analysis is very similar. So we applied our analysis to look at the case of if the signal that you're trying to denoise has multiple structures. How well does the combination of norms perform? And again, making a similar assumption to what we had before. So again, the norms are decomposable. We have S of them. And again, we make this assumption that the pairwise inner product between the sign vectors are positive. Then we have a lower bound on the value of the risk as a function of the regularization parameters that looks very much like what we had before. So it's actually a constant times, again, the minimum of the dimension of TRX. So again, your denoising performance is also stuck with the best among the individual structures. And it's not using really the fact that you have simultaneously these structures in the same object. This basically, a lower bound on error tells you your error cannot be better than this. So this is a fundamental limit. So I'm not putting the details. Alpha is again, a constant that involves more or less a constant, but yeah, it's bounded between 0 and 1 for all the typical norms. An example of this is, again, a matrix that is rank 1, so outer product of x and y, where x and y themselves are k-sparse vectors, and let's say they have unit L2 norm. And so we want to find an object that, we want to find such an x given a noisy measurement of it, which is x plus z, where z is IID Gaussian noise, again with entry-wise, each variance of each entry is sigma squared. So for this program, with two regularization terms, the minimax risk, so what is minimax risk? So risk was simply this quantity. Minimax risk is that you minimize this over the choice of lambdas, because lambdas are regularization parameters you can choose. So let's find the best lambdas and call that eta star. So the result says eta star is bounded between two values. So I haven't actually discussed the upper bound, but you can also prove an upper bound, and actually a similar upper bound was independently recently pointed out in a paper that I'll refer to in the next slide. So eta star is bounded by two quantities, and in fact, in many cases, these two are very close. So upper bound is minimum of k squared log n, and n times r. And the lower bound has L1 norm of the vectors x and y in it, but suppose, for example, these L1 norms are scaling as square root k. So for example, if the entries are plus 1 minus 1, then these would be scaling as square root k. Okay, so they're plus minus 1 over k. And then this whole thing would be scaling as k squared. So comparing this one and this one, there's only a log factor in between. So they're pretty tight. Question?
Sorry, what is R?
Oh, R is 1. Sorry. R is the rank. Good question. Yeah, in this case where this model is this, the R is 1. So that's just it. Any other question? Yeah.
So where is the worst case in this? What are the worst matrices?
For what?
For the minimax risk. So what is the worst case? Because if you have tight bounds, so probably you know where the worst matrices are.
I see. So among matrices that have this structure, is there a particular one? Yeah, I don't actually know. That's a good question.
Perhaps you know what is the worst sigma. I think typically the worst sigma is going to 0. That's the worst matrix.
That's
Since that
good
much-
to be true. Yeah, I haven't looked at it, but that's good also. But we know for sure it's between these bounds. But yeah, when are the bounds achieved? I don't know. The important thing is bounds are typically seem to be pretty close anyway. So it seems you're really sandwiched between, at least scaling wise. Your order isn't getting much better than this k squared here. So, and actually what we are highlighting is mostly the lower bound and the fact that you cannot push error to go very low or when you have this kind of combination of norms. So, yeah, actually, so this is a big topic in statistics, and some of you may know more than me. I'll be happy to talk to you more about it. Okay, so I'll give a quick summary, and then actually the next slide is going to be discussion, because I think that probably what I talked about opens up a lot more questions than it answers. So it's interesting and brings up a lot of things to think about. So the summary is that we talked about recovering a model given random measurements when the model is known to have several structures at the same time. Or in machine learning terms, you're talking about learning a model that has several priors, given several priors, and you have regularizers encouraging these priors, etc. So we have a general framework to analyze this kind of problems, and our result mainly says that a combination of convex penalties requires many more generic measurements than one would expect, than the individual norms would indicate. And contrast this to the situation with cardinality versus L1, or rank versus nuclear norm, where the scaling of the relaxation was actually very close to the true number of degrees of freedom. And that similar results extend to answering questions about denoising of simultaneously structured signals and statistical bounds. Okay, so lots of things to do. One of the things we are trying to look at more carefully is this issue of denoising and statistical errors, and what kind of bounds one can get, and how can one try to get better denoising properties. Another question that's quite interesting is that, okay, so if combining individual norms isn't a good idea, then what is a good idea? Should we construct another convex penalty? And to some extent, abstractly, that question has been answered in the work of Venkat Chandrasekaran at Caltech and co-authors, so Ben Rick, Pablo Farillo. They have a very nice paper that gives a general framework saying that if you would like to recover a certain structure, what you have to do is to construct atoms that represent that structure. So the desired object is a combination of a few atoms out of your atomic set. Then there is a systematic way to construct an atomic norm, and that norm is guaranteed to be to require minimum number of Gaussian measurements. So that's nice. That's a very nice recipe. But the catch is the following. So sometimes you cannot identify the atoms easily. And if you can identify the atoms, taking convex Hall itself is often a computationally hard problem. So in the case of L1 norm, that basically just amounts to take the corners, coordinate vectors, and then take their convex Hall. So that one was easy. But in many cases, forming such a convex Hall given a set of discrete objects itself is not easy. What it amounts to is that, yeah, there exists a norm, but evaluating that norm itself can be hard. So that basically says, okay, that's not computationally feasible, so what else one can do? What else we can do is that basically case by case, look at different cases and see whether some are easier than other ones. There is some recent work, for example, on very simple combination of norms. So elastic net penalty is a combination of L1 norm of the vector and an L2 norm. Now, L2 norm is not a very strong structure, but still, there are two different norms involved. And several people have studied when you add L1 and L2 norm, do you actually get the best behavior in terms of sample complexity, or is there a better function? And the most recent result is by Nati Cerebro, and he shows that no, combination of L1 and L2 is bad, and you can actually compute the correct object, which is a convex envelope of cardinality over L2 bar. So it's a little bit more complicated, but you can actually compute it. So in this case, one can actually construct the right object. There's also some interesting algorithm questions that come up. So if somebody wants to solve these optimization problems with combined penalties, what algorithms are good? And there is some recent work on that by Iyengar and others that uses composite norms and gives efficient first-order methods. So in this talk, I didn't discuss any algorithms, but there's some work on that. Another thing that's important is that in the motivation part, I used the example of sparse phase retrieval. But in phase retrieval, if you recall, the measurements were not random Gaussian objects that were acting on X. They're not inner product with random Gaussian. But they're inner product with AI transpose, right? Where, for example, one can maybe assume AI is a random Gaussian vector, but not AI transpose. So this needs a little bit more refined analysis, and there's new work by Voroninsky and Lee recently analyzing exactly these kinds of measurements. And interestingly, they also show that the number of measurements you need is lower bounded by something like what we have times log n, even though their type of measurements are different. But there is more room to actually study these kinds of measurements and answer questions specifically about phase retrieval. And finally, there's an intriguing connection to the problem of sparse PCA, which is the problem in which you would like to find the principal components of a matrix, but you would like the principal components to have as many zeros in them. So let's say, top eigenvector, but having a lot of zeros. So that would help you identify, for example, only a few of your variables or subset of your variables that are important as your main components. That problem has received a lot of attention, and it actually can be seen as trying to find a matrix that is, if you wanted to find, for example, the top principal component, then you will be looking for a matrix that's rank 1 and sparse. So we want to explore to see what kind of connections one can have with that problem. And so these are some references. This paper is the main one that's on the archive, and there's a second one that discusses denoising that will be posted soon. So, if you have so that's it. Any questions?
I have two questions. So you mentioned if the matrix, original matrix, is a low rank plus a sparse, then the combined norm works well. You have a norm on each of these.
Yes, I think that has been studied by at least one paper.
So
I
you
have
just
seen.
have, yeah.
Yes.
So now you are typing a problems. Is the matrix is both sparse and low rank. So you still use this weighted sum of the norms on this same matrix. So that's what you call a combination.
Yes, that's true.
Well, this combination be different.
So,
you
yeah,
prove some negative result. Sum is not working. To me, it's more like an and. This matrix is sparse and low rank.
Yep.
When you use the max of the two norms,
Yep. So actually,
So-
yeah, very good questions. But yeah, exactly. I mean, actually, in the
that's the
beginning.
do, right? Yeah.
So.
Instead, you talk about the sum, whatever.
There's someone we didn't talk about, but I
Okay.
don't have here. But in the very beginning, when I mentioned, yeah, there is like problems like principal component analysis with outliers. That one basically says I want to find matrix X, and X is L plus S. L is low rank, and S is sparse. So then the objective would be nuclear norm of L plus
Plus,
norm
yeah,
of
right.
S. Yeah.
But now, yeah.
Yeah. So that
That's-
seems
that's
to
right.
work fine in terms of degrees of freedom.
No, and right now I'm saying maybe you want to use, you take the two norms, which norm is too big, you minimize them, push them down.
But it's not
If
on
that
the-
become large,
It's not, we prove that it's not on the Pareto frontier, right?
no, that's to give a different frontier. Right? If you take max of these two norms,
Maximum. Okay.
Yeah,
We did look
that's
at the
what I'm saying.
maximum, but let's see.
so
Right.
basically you
So this second choice takes the pointwise maximum.
oh max.
So actually, for example, let me get to this figure. So here, you can think if x naught is on the Pareto
Okay.
optimal front, you can either construct a hyperplane that gives you those lambdas, or
Or
you can
these.
construct like things like this.
Yeah,
This would be the pointwise max.
yeah,
And if it hits in this point, then fine.
That's
so
right.
you can basically hit any
yeah.
point on
You
the
use
Pareto.
some weight, take the maximum.
Right, right. So with weighted max, you can also hit points on the Pareto curve. With weighted sum, you can also hit points on Pareto curve. But if you're not on the Pareto optimal front, then none of these will work, right? So if my m was too low, then Pareto front is here, and I'm expecting it to try to recover that excess inside the region.
So, okay, my second question is on the AI, which is your discussion page. So, so you mentioned that maybe AI may not be randomly generated, something like AI. So I have a problem, it's like a sensor network localization. AI actually have exactly 1, 1, and 1 negative 1.
Oh, I see. Yeah, that should be harder.
It should be,
actually, what I
any
have-
kind of analysis, if this 1 negative 1 randomly generated.
There might actually be something in phase retrieval literature. I'm not
Because
sure.
if you take
But-
AI like 1, 1 some position, 1 negative 1 some position, so you basically measure the distance
Yeah,
of the
yeah.
other 2 points.
Right. So I guess
if you
in
randomly select the distance, pair distance to measure, can you recover those things?
So that reminds me of, I have seen one talk recently on sparse phase
We
retrieval.
brought that paper
That's,
So,
with that.
yeah, I know.
oh, yeah.
But analysis is more, is completely random pairs or is the, is
No, it's not random pairs. It's-
That's right,
it is,
yeah, because you
generated
just,
graph.
like a unique disk
It's
graph,
easier. It's easier
unique
with
disk
random
graph.
pairs. It's much easier if you do random pairs.
Or random pair would be easy, oh, okay.
I mean, the analysis.
Yeah,
Uh-huh, okay. There's also some work in sparse phase retrieval also by Bobak Cassidy and his group that looks at samples of autocorrelation. And then they try to use this distance between the different samples to reconstruct
okay.
the signal. It's not like, it does not use a convex relaxation, it has its own reconstruction.
So just one more question. So you studied the denoising and the recovery problem, and there is this general conjecture about the relation a general conjecture by myself, David, Maryam, and Johnson, that the minimax risk is equal to the subsampling ratio. Do your bounds confirm this? And there is a recent paper by Joel Tropp and others that proves. I didn't read the paper, so I don't know what they prove exactly, but it proves that conjecture.
Yeah, it's actually very interesting and exciting. I know that actually Sonnet Oymak, who's at Caltech, our collaborator,
Yeah.
independently, he has a proof of this equivalence as well. But I haven't yet completely read the
Because,
details.
I mean, that would take away, you prove, n
You
bound.
prove
certain
one, then it
number.
translates
Yeah.
into the other one. So far we've individually proved the second one as well from scratch. But if you can use this equivalence, that should make it very simple actually. So I believe Sonnet has something on that. But yeah, I have seen you have an empirical work using message passing.
Yeah, and I mean, Joel has and others have paper, but so.
Yeah, it's quite interesting how there, I mean, even the proof techniques seem so related that, yeah, it won't be surprising that there's really an equivalence.
Any more questions? Well, thanks again.